thinking to muscle action to an action. This is what we do every single time. This also include our vision and other senses. For example, you are driving, you also see something coming towards you, you avoid that by steering away or by moving your bike or car away or bicycle away. Other senses could be senses of touch, senses of feeling haptic, and so on and so on. A standard system or standard CNS or central nervous system. But when I say BCI, what happened in the BCI? You have a thinking in your cortex, very upper part of your brain, and you bypass every single thing which used to be as a part of CNS and directly have an action. So in this case, let's say you want to grab a cup of coffee, you have a thinking about cup of coffee and you directly grab that cup of coffee, potentially in this case via robotic hand, of course, because that's where the BCI actually most useful, because if your actual hand is working or user's actual hand is working, they can use their muscle to do it. But let's assume a situation where this is not the case, then the direct brain signal can convert it to an action through a brain signal via a robotic arm in this situation. Professor John Vulpa from US defined a BCI as a communication system that do not depend on peripheral nerves, essentially your CNS. So that's the fundamental definition of BCI. Now I'll take you a little bit more complex version of the same definition. What you're seeing here is produced by me and colleague out there. We created a whole model, functional model, or in other word, if I want to define it, it's like a flow diagram of some sort, system diagram of some sort. So BCI system generally what it does, it take the brain signal. So if you see very lower part where it says user, take the brain signal while user is doing so many different sort of things. It could be related with motivation, it could be related with stress, mental workload, feeling sleepy, like a fatigue. It could be related with very useful, popular BCI phenomena. I will show you a couple of examples later in the slide. And those signals go through a device called acquisition device, which is a hardware, essentially collect brain data. And this acquisition device is generally either based on different kind of brain signal, because depend on what device a user have. Some of them, maybe you have heard this, something called MRI scans. This is a brain device which also can capture the brain signal. But there are some other ones also out there known as EEG, which essentially collect the brain data or electrical signal of brain data from the surface of the brain. So none of these devices need to, need a surgical operation. No, they all are can put over the head like an MRI scan. You just simply lie down in the machine and machine can scan your brain like an X-ray, but not really X-ray, but like an X-ray. And this signal, now you got a signal. Now it becomes very much like any other machine learning problem where you get a data and signal. And once you get this data, which is a signal, you can apply different signal processing technique. Now the word signal might be making a lot more sense for someone coming from digital signal processing, which is very popular in electrical engineering or communication engineering. And within that signal, like how someone, if someone deal with the data background, try to do pre-processing on the signal, like removing artifacts, removing the noise, or try to change the data slightly different way, and then extract the features of those data, features as in what you have to pick up to understand if someone in the stress or not, or someone want to pick up a coffee cup or not. And once you know those features, you can simply put a classification approach on the top with using machine learning with any method out there. For example, if I take a deep learning approach, in machine learning. That classification can classify, and once it classify, you can use that classification output to connect with an machine, which is a control interface. Now, in this case, could be a robotic machine or could be something more complex, if I'm making sense. Now, this whole process continuously run again and again and again when someone is dealing with brain-computer interface. Of course, it sounds like it's very complex in nature, and it is, because we're talking about neuroscience when we're dealing with the user. Um, oh, sorry. I think I stopped sharing, is it? I don't know,
Yes,
what
sir.
did I do? Oh, no. Okay, again, back to
Now it's
screen.
okay.
Yes. Yeah. So we have a whole neuroscience in here. We have the whole signal part in here. So very much about data and signal processing and feature extraction. Then we have about machine learning, which is classification. And then the last part is very much around human computer interface or control interface, where once you have classification in this part of the signal processing, you do that connection with um, uh, the user, how they can connect and do things. So this is like a more detailed version of what it means to a mean of a functional model or mean of brain computer interface. By the way, all the slide have a reference on the bottom, which you can refer if you're interested more into what it means. Like I say, so now green part is a user. Another green part, I call it transducer, which is essentially collecting data, processing data, classifying the data. And the last part is control interface. So basically three important parts: user for the brain signal, transducer to process data, collect data, and classify the data, and the last part, control, where everything start making sense for the user if the user is controlling this environment. Okay. In addition to this, generally when we do research, and there's always a two version of research most of the people apply, where they collect the data, hold that data in their computer, and run everything else there later on. So you can call that kind of work is the offline data analysis. And most popular, obviously, because not everyone have this equipment, for example. So you may need to go in hospital or some other research lab to get this data. Of course, then data will become offline. But what I do in my lab is mostly online, because we got some of this equipment, especially something like a EEG is there, something like a FNIRS is there, which is a different kind of equipment for this kind of research work. Okay, let me keep moving on. And of course, it's okay if you don't understand completely, but what I want to convey from this slide, this is how BCI looks like. Sounds very complicated. And it is complicated and interdisciplinary because we're dealing with the human, AI, and as well as HCI. Um, Now, in addition to this, once user controls something, user can see that information as well, which is very interesting, right? Because if user feel, oh, I try to control A, but this doesn't work, then it make user feeling frustrated. And if it's frustrated, then the signal in the brain also change, which is very interesting phenomena when we're dealing with the BCI. And because signal change, then it affect the input again and maybe even become worse. So it's like a closed loop. Again, more and more frustration, and user in the end after a few minutes like, oh, I don't want to use it anymore. So that kind of challenges when we're developing a BCI system as well. A simplified version of what I showed you is this figure where you acquire brain signal, in my case, mostly EEG, which is an electrical signal, look like this. And pre-process those signal, of course, pre-processing technique, extract neural feature, which you want to target on, apply a machine learning method translate those method into a matrix of some sort, like a binary matrix, 0 and 1. 0 means go, 1 means don't go or opposite, and then use them to control different things, either robotics arm, computer, virtual reality headset, and so on. And this could be in the closed loop manner. This is another simplified version, what I defined in the previous slide. One second. Okay. So total 6 step. Now, I am keep mentioning BCI because from last few years, of course, AI is everywhere, which I think all of you know. But the BCI same time growing so fast. And why is growing so fast? It's not only because so many researchers working on this, not because so many researchers working on this field, but also some big companies get involved in more work, more research, as well as creating product out of this. Because of course, company putting money into doing this kind of work means there's a quite a potential in this. And when I say companies, I'm not talking about just any company. There's so many startup, no doubt in it. But when the company like Neuralink, which is a company from Elon Musk, and which is a company from Elon Musk, and there's several company from Elon Musk. There's a several company from Elon Musk, like a Tesla car, if you know what I'm talking about, SpaceX. So quite successful. He is probably one of the richest person in the world. He have another company called Neuralink, which is specifically about BCI. Although the BCI Neuralink company is not the same kind as I'm talking about. When I say same kind means in his case, that information has to be implant. So head need to be open and our neurosurgeon have to put the chip inside. So a little bit more complicated. But what I want to share here is so many company also want to put an effort to create more BCI. Just similar to Neuralink, almost same competition. There's another company called Synchron, which is from Australia, also developing a sensor, but does not need a surgery like a Neuralink, but a little incisor on your in on the vagus nerve, which is on the neck, and they can put the sensor through it. Okay, so these companies are very invasive, so they need a little surgery of some sort. But there are companies who does not need that. For example, Neurable. This company is there from last few years, and they're creating headphones, very much like you may have seen and maybe using it. And um, within these headphones, you see this little black and white band on the headphone. This band essentially able to capture the brain signal and give you information like a monitor your brain signal, that how are you feeling, or if you're under stress, or if you're feeling sleepy, or if your attention is dropping, and in fact what's your brain age and that sort of thing. So lots of things happening. So it's a very exciting time for people like who do BCI research. At the same time, like I say, not to mention what's happening with AI as well. Now, why I'm mentioning this big name of company, one additional name I want to mention, actually two of them. One more is Apple. So Apple, which is largest company in the world, also in putting a lot of effort to create more BCI within the Apple environment. So that's so exciting again, because again, what happened when companies start doing such kind of work, especially big company like Apple or Neuralink, as well as Meta, which is a Facebook in the past, then the whole research world start jumping on that and start moving beyond. And maybe that's a reason from last few years this field become so growing so fast, including growing a lot in India itself. So lots of startup, lots of company, lots of researcher as well. Okay, so just touching a little bit more on devices which I just mentioned, right? Specifically, I talk about EEG, which kind of will look like this if you see on my screen. So it's like a head, it's like a cap you can put on your head that has a smaller sensor which look like this, and this sensor able to measure micro volt of electrical signal, very very sensitive from the brain signal when you're doing something, thinking something, or want to act, or you have some cognitive state like you're feeling sleepy, feeling stressed, feeling workload, regardless. I mean, so many potential reasons. Of course, when we do research, we start with this kind of a sensor, but then once we go and try as an application, we want to use a smaller, more simple sensor. For example, something like this, which is a Muse system, uh, not so expensive either, or something like this, which is created by us in the lab, in the blue color here. These are more look like a headphone, right? And of course, there's a trade-off. You use this fancy, very ugly looking system to more fancy, sleeky design. So there's a trade-off what you can do with these two. Of course, when we do a study, when we do experiment, we use this complex one. And when we study complete, we know what we are doing, then we can you start using the smaller sensor like this. And of course, there's a big trade-off between them. One trade-off, for example, is signal quality. If we use this kind, signal is very, very good. If we use this kind, signal is okay, okay. Just do our job very briefly. But if we talk about comfortability, of course, this is not so comfortable system. And they are more comfortable, more easy to use. Same time, cost-wise also a lot inexpensive, a lot more cheaper. I'll give you an example. This is a great example of BCI, which is just from last year. Oh, no video. Okay, never mind. It's not playing, but I have a few more videos. So let's look at this video. By the way, if you have any issue with the flickering light, maybe this is not a good slide to see. So please ignore and move away, look away from this slide until I sharing this couple of minutes. In BCI, there's a phenomena called SSVP, steady state visual evoked potential. Essentially means if I show you this flickering light, I'm not sure if you're able to see on Google Meet or not, your brain will produce same entrainment in the backside of the brain. And if you record those signals using EEG, you can predict what is the frequency of that information. So if I show you 10 hertz, means 10 time on and off, and I put the sensor on the backside of your brain, I can also measure that you are looking at the 10 hertz. And just by doing so, I can classify a bunch of different things. For example, this video. In this video, user is wearing a EEG headset on the head, just few sensor, and it's connected with the robotic arm. And user have to pay attention to one of the option on the screen. Each option means something related with eating. And once user pay attention, machine learning decode that signal and feed that signal to this robotic arm. For example, now option selected is drinking, and robotic arm will execute that command and provide that input to the user. So that is what we call brain-computer interface. Very quick takeaway, but you get the idea, right? This is a demonstration that was possible with this kind of a system. And again, the flickering I'm showing, like I said before, is the flickering, what we call SSVP. And depend on what SSVP you're using, you can have as many as you like. And it just create a very great kind of a BCI system to play around. Now, when we're dealing with BCI, one important thing happen all the time. Like I said in some of the previous slide, The sensor user putting on the head are very sensitive. Microvolt. It's not even millivolt. It's a microvolt. That means even a fan is running in your room, or even you are using a charger in your computer, if those signal also create a little microvolt current, and those sensors are able to pick up those currents. So we have to create some algorithm to deal with that kind of a signal issue. So this is one of the work we did where we try to improve the quality of signal. So what you're seeing here on the screen, we created more like a computer vision approach to deal with the signal quality. And this signal quality, especially if you see red and blue, red signal is what is the input signal, and the blue is what is the improved version of the red signal. And we find very useful result by just doing so. And we can do this in the real time when we're doing the BCI. So which is very important before you run the machine learning algorithm. Another example is AI based approach or reconstruction approach. So what we did here, we take the original signal, which is EEG, apply some technique, in this case CCA, or in other word is known as a canonical correlation analysis, and use this to information to generate a new signal. Or in other word, I call it reconstruction and enhancement. And by generating the same signal, very similar, but without the noise, without those extra noise I'm getting from environment, I can get this signal and use this signal for BCI again in the real time. Again, I'm keep emphasizing this real time element because that's very, very important when we do this kind of research work. Okay. Um, Now, if I show you a bit more, I mean, this slide not so important, especially if you don't have any background in this field. Essentially, I'm showing here before AR. AR means automatic reconstruction, and what happened, and after AR, what happened. So signal quality preserve. Essentially, this result trying to show that I apply my manual approach to remove the noise from the signal, and then I apply my automated AI-based approach to remove the noise from the signal. Before and after signal is almost same, which shows that my approach of AI-based is correct or it working fine. For example, the most simplest way you can see this result is, for example, this red and blue line. Blue is the original, how it should look like, and red is what is generated. So you see they are very identical, especially toward the feature part. And this is the feature of the signal. Again, this one is another example where I'm showing this information. Couple of other example on the bottom. So this A, B, C, D figure essentially showing different kind of neuroscience phenomena in the brain signal. And I'm showing before and after applying AR, it preserved that information, which is excellent. And you see, this is the work from 2018. This is the time when AI is not so popular yet. AI became so popular, especially generative AI or large language model, since, or I should say after COVID, when AI model are there and it just starts disrupting everything. Now, what I think, what I want to share, what based on this BCI, because I want to give you a little introduction as well, because I'm going to talk a bit more about brain and BCI in the following slide. I think when we're moving ahead, in fact, now already, we are dealing with three different kind of future of research. One is agent only, which is very much like how AI work at this moment, like a large language model, like an OpenAI or ChatGPT, like a cloud out there, or like a Google Gemini out there. They allow you to do research, and they can do lots of automated research. For example, OpenAI as well as cloud as well as Google, they all allow you to do deep research or deep search which is essentially a whole literature review, which you might have done if in your PhD in the past, or if you are doing PhD, you might be doing now. Of course, the quality of work may not necessarily same as a human written, but it's very helpful. You spend a months to looking at paper and summarizing things, versus agent only approach can do it for you right away. That's almost like a great example of what's possible with AI. But I also think this is not the best approach either. It's a great approach. It do a lot of things. Some example I listed here: AI scientist, agent laboratory, or Google co-scientist. I'm gonna share a bit more on a couple of these examples. They can not just do literature search, but also can write code, run experiment, draft papers even, which sounds very scary. Because it's like a whole PhD work is all just disappear, or RA job or research assistant job doesn't need, because maybe they spend a month and get salary just doing so, and the AI can essentially can do that in few minutes, or maybe hardly a day, uh, with a fraction of the cost, right? Then there's a second example of future of research, which I think is the important, and that's where my BCI comes in, is a human and the agent. Now, by the way, I'm using the word agent, which equal to AI. So don't be confused. Agent is AI. Agent could be human as well. But in this case, agent is AI. Now, human and agent is the approach where human and agent work together. And I think that's the best approach someone can deal with research. And I think that's a good approach we should do as a research, where human is involved closely with agent. It's not just prompting the AI that what to do, but essentially go back and forth, like you're working with a student, and develop ideas, develop hypotheses, and run experiment, and so on. I have a more to share in the following slide on each of these paradigm. Last one is a digital human plus AI agent. Now this is evolving field. There's not too much is there yet. But some of the work we are doing in the lab still so early. I'm literally sharing it first time ever in this presentation. So it's so that much early. We just still conceiving this whole thing together. And lots of some of the work also happen out there, but also very less, not so much. In this case, human is also digital. So human become a human, is a version of AI in a way, but it's a human AI. And then you also have AI agent on the top to conduct the research, which is interesting because you are providing human feedback like you are doing here, but you are doing digitally. And because human have limitation how much they can work, in this case, there's limitation disappear. And human and AI collaborating, but at unprecedented level, which I don't think we can imagine at this moment, and where this might be. And this really, if you think about it, it's really threatening the whole researcher actually, academic as well. But we'll see about that, what can be done. And I have some my opinion on that side. So let's start with the very first part, which is agents only. What's going on in this field? What is agent only approach? Um, like I say again, agent only approach is approach where we're dealing with AI based automated research, which is I think is already current way of doing research of so many researcher. And when I say so many researcher, I see lots of paper published, for example, from China, and lots of paper. You can the publication rate is just so fast that it make you wonder if it is from human or is really AI generated paper. And there's a highly likely they are AI based or AI code generated paper. And that's essentially the world we are in, where the agent only research is what pushing ahead. And there's a conflict between AI based generated research and what existing rules and regulation out there at the university level or at the government level. They are not able to keep up researcher progresses. So there's little loophole at this moment, which so many people try to uh, maximize the research output. So let me show you. Generally, these research, but which I call AI agent-based research, is look like this. Um, there's a part where it has some input, so essentially initial plan, which is essentially prompting from the user. And this prompt, essentially what it does, it generate the code, it run the experiment, it create even plots, graphs, figures, and then go back and keep running again and again and again until it reached the point where it looks like an original idea, original output, and it even able to generate a research paper. So terrifying, right? Which is funny because it means that a research assistant, like I said before, right, or PhD student work, PhD student might be doing. Maybe they are doing this way. If they are not already, they are missing out some of the advanced research work they can do. Now, plus point of doing such kind of research work is you are not able to just do the research, but you can have multiple version of the same work to choose and critically evaluate what's the best way to move ahead, which is unfortunately not possible a few years ago, where human have to do all manual work. Means they generate the code and run experiment, then look at the figure and they're like, oh, it doesn't look good. By that time, it's already more than 2 years, and they're like, they have to complete their PhD. And so they quickly go again, maybe a smaller experiment and try to wrap up. The same process, instead of few years, it could done in a 24 hours or even lesser. So that's the kind of a computational research happening. I'll show you an example. This is an example from a company called Sekna AI. It's a Japanese company. This is from their paper in 2025, just last year, where they showed and demonstrated how their model can be used to do everything. So it's very agentic AI approach of doing research. You provide a plan, innovation, and idea, higher level idea. In fact, it can even generate idea for you based on the keyword. It look at the novelty check of that idea based on existing published research and try to do the score of those idea, archiving idea. And once it's a score, it go into next step. You provide us some sort of experiment template. It can generate code based on experiment template, create code, execute the script, and continuously doing this experiment and update the plan until it reached the optimal point of very good result, of course, based on novelty here, and generate data plots, so figures. And once figure are there, this figure essentially can be used, this whole output experiment, which is essentially equation, code, algorithm, and the plot together with the idea. It has all the things needed to write a manuscript, which it can produce the manuscript, and not just can produce, it can review the manuscript and go back and to plan innovation and reprocess the whole thing. And we keep doing this whole closed loop version of a paper write-up until it feels satisfied based on certain scores. In this case, novelty check is one of the big score. And they demonstrated last year that this is, by the way, this is all open source, anyone can access it. But if you're a PhD researcher, I do say you go and learn what this about, but do not generate paper through this. But of course, use as an assistive tool if you like. So this all published, is all available online, and anyone can go and utilize it. And like I said, example in the previous slide, lots of paper coming through from country like China and other place. And there's a good chances they are utilizing things like that. Show you an example. These three paper I pasted here, but there are two more. If you go to the website, is full on generated by AI. Now they are machine learning paper for some of the top machine learning conference happen out there, like a Neuro IPS or ICML. These are two number one conference in the world where pretty much all important machine learning model is come from, and their model generated these very novel ideas. And these papers are preprint, obviously. You can even go and read it. Of course, they did not submit this paper anywhere, but they just want to show that capability of their model is superior. They can do whole research, create new model, and then you can feed that model to update their language model as well, right? So sounds like really a future we are sitting on, which is in some way we are, right? We are really interesting timing at this moment where we have so much progress in AI, and of course, unfortunately, lots of strange thing also happening. So this is Sakana AI from Japan. I want to show you another one. This is called Google AI Co-Scientist. Keep eye on the word co. And I like that part because essentially it doesn't get rid of the human, but human is involved here. In this case, human essentially discuss through the chat those ideas and try to go back and forth with the ideas. Like I think some of you might be even using LLM or ChatGPT or Cloud, for example. It create a research goal, which include add idea, review idea, discuss research, and based on that, it create a research proposal. And again, very similar to Sakana AI. Uh, we got some noise in the background, I guess. So it go back and discuss those research proposal, create a top rank research hypothesis, very much like Sakana AI, summarize them in the research overview for human to also to understand what's going on. And once human understand and say, yeah, go ahead, work on it, then AI co-scientist, which is a Google AI model, take that research into generation agent. And I'm not going to go on the whole step here, what's happening, but essentially it simulate the review, it verify things, it write code also like what we have before, it do meta review, which is essentially like a reviewing a research paper, and keep repeating this step. You see this little closed loop circle you can see here, until it reaches the point where you see it keep ranking output, which is generated through the research, until it reached the point where the research looks like a valid research, and share it to user. So like it says here, AI co-scientists continuously generate, review, debate, and improve research hypothesis and proposal toward the research goal provided by the scientist. And scientist is us. And Google AI is your supporter. Now, if you look at this, you're like, oh, maybe I don't need RA anymore, and I can just use this. And in some sense, it might not be wrong either. And of course, once it generate all these things, something like a co-scientist, which I shared in the previous slide, also can be used to even generate code, execute things, and go ahead and complete the whole research. Another excellent work happening in automated research, and that's actually another future of research. Now these all future are not the future anymore, they are the present, they are at this moment. People can go ahead and essentially try this, and like I say, I believe lots of students, especially new students, are already might be using it, some kind of model like that. So as a researcher, as us who already went through that complicated step, might want to think about how to strengthen our strategy of do research as well. And doesn't mean we get rid of this model. I want to show you a couple of other things from the same model. Google, this is published paper, they evaluated their model and human. So they're comparing human and AI here, okay? And try to understand if their model is really doing good job or not. So if you see this very first graph where I'm moving my cursor, so this blue one, which you can see increasing line, is AI co-scientist, which is essentially Google AI doing the job. and, and all the flat line, including human, is exist here. Looks a little sad, I know. So unfortunately, we are here, and that's how much hypothesis and research proposal we are able to come up with our brain signal, whereas the AI generating a lot better uh, in this way. They're using something called ELO, which is a kind of a rating method to calculate the relative skill of a user. So here, co-scientist itself is like a user, and human expert is this red. They're also comparing their own model, like a Gemini 2.0, which also somehow almost there. Unfortunately, human is the lowest one, followed by AI model, and very top one is the best model, which is of course AI co-scientist. They repeated this again, 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 and just look at the top 10 average. When they did that, they find AI co-scientists initially bad than even the human or any AI, but then after certain repetition, it just improved a lot. So again, it's showing you that how well a co-scientist can do the research job. Sadly, uh, I mean, not saying that it's replacing human, but who knows, right? It sounds alarming. And you see, human doesn't really improve much. Or I should say, the improvement in the human by repetition is not a big jump. I do question here who are the human expert they invited in this work, because they're really not performing very well. The last part, they also look at if their AI co-scientists, which is a AI-based research, does it really, really compare to all state-of-art machine learning model out there? There's no Sakna AI, strangely. I wish they did also that. And of course, lower number is good, higher number is bad, by the way. So obviously, AI co-scientists perform the best. Closer to 1 means very good, and more higher is a bad. OpenAI O1, which is old model, performed 2.45, Gemini 2, 2.45, Gemini 2 flash thinking. I mean, these all are a more AI model. And of course, AI co-scientists, again, able to show pretty good result. They compare this all into there's a there's a benchmark they use all the time. That benchmark essentially means high potential, I mean lower ranking equal to high potential for novelty and impact. And like you can see, results so far show pretty obvious output, right? Okay, so this is the state of art, what's happening with the research world in agent only research. And this is all last year. We are in 2026. So what it means that we have to keep up, because especially AI model, pretty much every other month you have a new one. And because they are so fast in progress, the human are slowly and slowly going behind what they can use and adapt to them. And that's the reason some of people have even no idea that many models are released here and there all the time, unless you're directly sitting in the middle of everything happening around the world. So that's sad, and but same time promising. It just kind of changing the whole scenario how we do research. I also want to share this table, which shows the several similar model and tools out there at this moment. It's very, very selected one, covering things like AlphaFold. I'm not sure if you heard AlphaFold before, but this is like one of the first AI model created ever, uh, which allow protein structure prediction. Now, who's doing research in biomedical or bioengineering, as well as potentially chemistry, it might related to them, AlphaFold model. Now, this is from Google again, surprisingly, not so surprised, or I should say Google DeepMind. And this model, the people behind this model even received Nobel Prize in 2024. That's the first ever Nobel Prize. Actually, few people received Nobel Prize in AI field ever, which happened in 2024. Additionally, like I say, co-scientist is really doing very good job. But there's some other model as well, like a Elicit, which is like a research assistant for doing literature review. There are OpenLX, which is knowledge graph generation, which is very helpful if you're doing research because it can generate a knowledge graph and let you synthesize what you're reading, what you're understanding, what it means, what it does not mean to adjust and uh, understand the ideas of state of art research work out there before you start conducting your own research. There are tools for automation as well for the whole lab actually. There's something called SnakeMake and Stratos. Both are in some way generate pipeline and data analysis pipeline, multi-step automated. I haven't used myself, so don't know how good they are. But this is just some example who already telling you there's so much thing possible. This Stratos, which is cloud lab automation, is a robotic lab-based infrastructure where essentially you can think of how experiment also run by robot or agent in this case, a physical experiment, not just computational experiment. Then there's a R&D platform called Benchling, which also do very much similar to all other model experiment data, protocol, sample, like workflow automation. So these are very much applied to labs. This could be mix of robotics lab, wet lab, or something along the line. But among them, I think the first four might be most interesting, or at least Elicit, OpenLX, and Google AI scientists, they are doing pretty good job. And not to mention Sakna AI, which is not a tool, by the way. These are the tools which you can download and sign up and use. Sakna AI is more of a research output so far. Maybe they create a tool very near future as well. Okay. Any question so far? I happy to take before I move on to next step. If not, that's also fine. You can always address all the question toward the end. Now, moving to second part, which is maybe where I sits on, collaborative human and agent. Now, whenever you say human, obviously brain become the central part here. And like I said, that's where I sits on, where I want to give you some example, not exactly automated research, but along the line, which we are trying to do at this moment. And hopefully it inspired you some idea for yourself as well. There's something I want to explain first, collaboration between AI and human through use of BCI. BCI is again, brain computer interface I shared in earlier slide. And I'm going to talk about one special kind of BCI, which is called neuroadaptive BCI. So not just any BCI, but something which is neuroadaptive, means it adapting from the brain. And that is what collaboration here is all about. This definition I shared you before, which means BCI is something where communication system happen without the need of peripheral nerve. But the updated definition, if it's a neuroadaptive, is you adapt or adjust the functionality based on the user's cognitive states. So when user feeling sleepy, when user feeling stressed, when user feeling overloaded, when user exhausted, when user mind wandering, cannot focus, when user is very focused, and so on. That's the cognitive states. I mean by using that information to adapt, to collaborate with AI. When I mention this, this is just an example of some of the things we do in the lab. It could be brain control robot, you just saw in the slide. It could be something about gaming. Gaming, by the way, gaming is an excellent way to understand human. It could be something about human agent teaming, where agent is a robot. It could be about virtual reality, mixed reality. It could be about air traffic controller in this slide, which I'm not sure I have video, but I will see if I can show you. Or it could also about one very important research word called spatial navigation. But the idea behind all of these to use AI and the human to either replace, restore, or enhance human being. By the way, when I say replace, not replacing human, but essentially providing user some sort of ability to replace their existing. Let's say they cannot use the hand, they can use a robotic hand to do things. Now, when I talk about this kind of collaboration, essentially it means you continuously monitoring the brain signal and you continuously adapting to those brain signal. Now, this adaptation could be happen for the research, like its little icon here, but this also could be happen for all sort of other things. It could be happen for self-driving car, for example. I'm not sure self-driving car available everywhere yet or not, but self-driving car can sense the brain signal and can drive user accordingly. Or it could be happen for a robot. It could be happen for your computer, which you may be working in an office, and you getting a lot of tasks from your supervisor potentially, or maybe in the office from your boss. And based on the brain signal, those tasks just adapt and present in a way that become more easier for you, not just easier to complete, but also be more productive. So that's a kind of a collaboration I'm talking about in this situation. So let me show you one example. This is the work where we did the collaboration between human and AI. Now, as you can see this picture here, obviously this is the human uh, with the EEG on the head, same EEG I showed you in the previous slide. And this is a robot. This robot, the name of this robot is Anbot, ANBOT. What it does, it has a nozzle here, as you can see. It it throw a sand on the wall. So it's a manufacturing related robot. It's not a robot like a human looking. It throw the sand from here with 30 to 40 Newton power. So it's a very strong force. It throw the sand, and it throw the sand so that let's say there's a wall have paint, the sand can remove the paint from the wall very easily. That's where this robot is used. Now this robot itself is very intelligent, so it uses bunch of sensor to understand the environment, also protect the human because it's a lot of force. And when human is holding this robot, human does not even feel that such a force is coming out from the nozzle of the robot. So this is the um, behavior of this robot. So robot have some intelligence, and now we're dealing with the human intelligence, and they're working together. We did some experiment to see if I can use a brain signal to kind of link this agent, which is a robot, and the human together. We conducted experiment with like more than 20 people, asked them to perform a task, and we recorded their brain signal while they're doing it, and we develop a model. We develop a model called reinforcement learning, very popular when someone deal with a human robot collaboration or human agent collaboration. So in my case, I use a model called DDPG model, which is a model deterministic probabilistic Gaussian model released by Google. So you see machine learning model nowadays, it's all come from companies like Google and Microsoft and OpenAI. And I use this model and use the robot signal. So robot also have its own signal, or you can call it brain signal in some way. Robot have position, where they're located. Robot have velocity because you're moving around. Robot also have force because robots have some force from the nozzle and also force back to the user. So I can use this all information and the brain signal together to train a model in a way that minimize the like a what I call conflicting feeling from the robot. Now, what is that feeling means? It's one of the cognitive state. It's a feeling when the robot feeling, oh, this is a feeling when user feeling this robot is not compliant. It's not following the user as expected. that feeling can feed into the robot, and robot is like, oh, I know user not feeling well, maybe I change slightly my speed, or maybe change my position slightly, or maybe change my velocity slightly, in a way that minimize the user bad feeling of cognitive conflict. So this is our example of a collaboration between human and the robot. I show you an example video what it does. By the way, when I did this, what we did everything online. So it's a closed loop. This brain signal feed into a model, it extract the features. Then I created a CNN model, which is a convolution neural network model. And this model try to predict the cognitive level, and this cognitive level transfer into a reward, like a positive and negative reward, which is very important in reinforcement learning. And this reward feed into what I call experience replay, where it feed into DDPG model, which is essentially actor and critique reinforcement learning model. Um, Very special kind, where actor try to optimize everything, where critique try to critique the optimization. So it's very much like how I showed automated AI before, where automated AI try to reevaluate the performance what generated by AI. Same goes here. Actor generate an output, and critic try to evaluate if that's a good output. If not, then you go feedback and it just keep running until produce a good result. And when this happen, it feed into the robot, and robot beings become more compliant. Robot follow exactly how user interested in very short amount of time. This is the video how it looks like. I'm not sure how well you can understand what's happening, but this is the robot user is moving, and we ask user to perform a gamified task going left and right, and user is using EEG signal here, you can see, and we continuously recording. And robots slowly become compliant over time as user move. Better example, if I give you, is um, by doing such an approach of human and AI collaboration is essentially when you're learning something, let's say a bicycle, and maybe you need a 3 day to learn a bicycle. Using this approach, maybe that 3 day reduced to 3 hours. That's what is doing, what's happening in here. So someone who can use this robot I showed here with very good training, very well how to control, versus someone who doesn't know the robot, they can use this kind of collaborative approach to reduce the training time, reduce the learning time. Some of the result from this, and this is again closed loop model. Brain signal, extract the feature, train a model on CNN, apply DDPG, control parameter of the robot, send that information to agent, which is robot, and then user again looking at that, right? So user also can get that information. That will also help the user to change the brain signal again and just keep rotating again and again and again. Of course, in this research, I look closely what's going on with the brain signal, and I found a positive result. Essentially, the information in the brain is over time going down and down, which is a good result, means user feeling more and more comfortable. So this is called power, like a brain have different kind of power, alpha, beta, theta, and delta. And I'm just looking at all those. And you just want to focus on theta, which is most important one. So it was this little red here, that was where it was originally, then reduce here and then reduce a slightly more, which is a very favorable output. Same goes to here. This is the whole brain, where this is the nose here. So it's like a top view of the brain, and it's slowly more and more reduced. So see, more red is disappearing, blue is coming more, which is good sign. Okay. We also look at if robot is doing okay. um, so T1, T2, T3 means T1 is very start of the session when we do experiment. T2 is the middle of the session when we're doing the experiment. and T3 is that toward the end of the experiment when we're doing experiment. So of course, these information also keep changing over time, which is also very favorable for us because that's what we expected. Any questions so far? I know this is very brain thing, but you get the idea. What I want to share that how human brain can be used to provide a feedback when you do automated research. And what we did so far is mostly around collaboration. And I believe this collaboration can apply to automated research very same way. So you can think of a system, something like a Google AI co-scientist, where the brain signal is continuously adapting and feeding the information to the system that your co-scientists essentially understand what you're expecting and just continuously modifying it again and again until you get the result which make you most comfortable and which is make you most favorable toward the system. Some other example which I can show you actually. This is example of a air traffic controller. I show it always. Wait, let me try. So you see the screen. Follow with me if you can. And in the screen you can see lots of red dots, but you also see there's a one blue dot in the middle. Now what happened when I start the video, the blue dot will change and become red. Try to follow it as good as possible. After this one finished, there will be another one where will be 3 blue dots. Then there's another one, there will be more than 3 blue dots. And that is how air traffic controller do their job. So let's try to follow it, okay? So I'm gonna start the video, try to focus on the blue dot. When it becomes red, keep eye on it. Oh. Okay. Let me try to play it because it doesn't let me play. Okay. So blue dot changed to red, and I believe you're still keeping eye on it, where it's going. Although everything also look red. Do you know the answer? Okay, that was the answer. I hope most of you got correct. Now let's try with the 3 dots again. Three dot already mix up, and maybe when I'm speaking, that also let you lose your focus. But let's see. This is already relatively easy one. Now this is very difficult, but let's try. Some of you may be able to do that. There are total 5 dots. Can you keep eye on all of them? I think you already might have lost all of those dots. I'm going to stop here because that can become very complex task actually. Now, in this case, you see what happened? Dot is still blue. The reason is what we did, we put the collaboration element here with AI. AI is the agent in this case, and we continuously monitor the brain signal and feed that information to AI, telling AI that human cannot handle that many dots. So please provide answer to this dot or try to find an answer. In this case, we are using cognitive state called cognitive load. So we know that user is feeling very high overloaded, cannot handle this kind of situation. Now these dots represent air traffic controller. So what air traffic controller is the same person. If you go airport, there's a big tower there. They keep eye on all the airplane going, flying in and flying out, and they essentially give an instruction to those airplane, telling them when they can fly in, fly out. And unfortunately, in addition to the screen on the dashboard they got in that little tower, they generally keep eye manually through the binocular. Plus, they cannot make a bad decision because bad decision means a fatal accident of the airplane. So it's so highly demanding job. And this experiment we did with the air traffic controller tried to provide them a system that can allow the AI take over the job when needed. So that's the idea here. So when human brain cannot handle anymore, AI just start making decision for the human. Now you would wonder why not do AI can make decision in the start? Because of the risk associated with AI. What if AI make the wrong decision? So it's a kind of a question, right? So is AI is a good or bad kind of a question? And so far AI is so far still not acceptable in this kind of a domain, but it can provide a suggestion to user. So you see user is still choosing these dots. It's not chosen by AI, but AI just try to simplify this information for the user so the user can perform this task bit better. I'm going to skip this one, not so important in this context, but this is another example of AI and collaboration. And this is another example of AI and collaboration for the people on the Navy domain, if, where AI and human collaborating, and with the brain signal, we can change the information shown to the user depend on how good and bad they are feeling. Now, it may not nothing to do, like I say, directly with the future of research, but angle I'm trying to portray here to all of you that how brain signal can use in collaboration with AI. This is the just one setting. It could be any setting where the brain signal can be used for driving the AI in certain way or even collaborating AI together. And I think that's the best move ahead, moving in the direction of doing job in the AI. So if I show you what's happening here, I'm representing this. This is the shape, and you can see it's in virtual environment. So user is putting an headset on and essentially piloting this ship as a captain. While this user is seeing different information on the screen, this information include. Let me pause here. Um, a little map. Um, Little map here. I'm not sure if you see. Yeah, you can see. So this little map here, which is essentially telling them where is a ship, where is a different obstacle. They see these little yellow arrows, which essentially telling them where is the other ships in the water. They have little radar. It's not radar. It's like there's a compass here which telling them is north, is west, is east, and so on. And there's a little radar as well, where this centered angle is the ship and showing the arrow where they are looking in this which direction, plus the speed and etc. Now you're wondering why this information is there. So just want to add here, when a captain in the ship, this ship is a special kind of a ship, by the way, is there, the captain or officer on ship who's in charge of it have to read all this information all the time to make a decision how to go and navigate here and there. And I think this example fits very well if you following the news of Strait of Hormuz, what's happening in the Middle East. And I believe the ship owner there who's moving from that little area have to follow this as good as possible to avoid Iranian ship and American ship and maybe some other ships who are there. So clouded, so much traffic is there. And ship doesn't drive like a car, so you can't just put the brake and stop. It slowly build up momentum, so it take a time to make a decision. So you have to make decision ahead of time. And this is one example. Now this is one of the way how user can see the information. I call it head up in front of the user looking at the information. Or user can do this. I'm gonna go back in the video to show you what I mean, which is originally how it worked. So user is just moving around in the shape, and you see how the whole screen, every screen is different place, and user have to go there to check the information and then come here to hold the helm. Helm is the steering for the ship, and to make a decision. Very complicated. User have to go back and forth all the time. Then I have another option which look like this, where user can see all the information in front of the eyes, like I told you before, which make things easier. But you see so much information happening for the user, which is okay, maybe in certain setting, but not always. Then I have third option for the user, this one. Now in this one, you see it even more simplified. There's no map here. Map doesn't need it. Just user focus on which direction user is going and which ship to avoid. Of course, user can see those shapes from the screen, but this give him enough or give her enough information where to go and how to go. By the way, those circle you see in the red is the shape user has to avoid. They are the bad shape, for example. So this is another example of human AI collaboration, how it can be done in such a setting. Okay. Now move on to third part. How about digital human, not the real human, and AI as an agent for doing research. Now, this is I don't do, but I came across so many interesting work, and I really want to share. And this is where I think future is moving. And this is something in our lab, on my lab, we started to play around. Now, what is the digital human? First of all, digital human is nothing. It's not human as such. It's a more of a human brain I'm talking about. You can also call it virtual brain. So it's all about, can I represent the human brain, digital twin of the human brain in as a virtual brain mathematically? So if it's possible to do that, essentially you get the representation of the human brain, which can be used as a virtual brain or virtual human. Now, some example if I can add here, is from the same paper which I put this figure on. If you want, you can have a look. Um, this is some representation by predicted model, digital twin. So they try to map the digital twin based on epilepsy, which is one of the brain disorder, Alzheimer disease, very common old age disease for individual, aging, when people get older, people start forgetting things, people are a little more grumpy sometimes, or multiple sclerosis, Parkinson's, schizophrenia, depression is another one. So mathematically in this paper, user is able to create a virtual brain of all these different uh, human brain. So you get an equivalent human brain of where the human brain should look like. Now assume this one, maybe before I go there. Now take that human brain and put this human brain into simulated world, right? Now simulated world is also simulated and human brain is also virtual. Now simulated world could be AI based world and the human brain is the virtual one. Now virtual brain go into AI world and try to interact with the virtual world as well. While interacting, based on this predicted model, you can predict how the world should behave and how the brain should behave. And based on that information, your virtual brain and the AI agent together can generate some output for the user to perform a research. One example could be of this kind of a setting is where the user is doing a research of checking how good this given medicine work on a human, and if human can perform the daily task normally. Now it can take that virtual medicine, well, medicine phenomena, mathematical representation of medicine, feed it to virtual brain, put the virtual brain to virtual world, and just wait and see how every interaction could be driving, walking, swimming, interacting with other virtual brain. So it's a social element. There's a physics to it. There's a water. There's a air. There's a breathing thing. So it as much as simulation as possible. More into it, more is better. And in the end, maybe within 24 hours, you get the result. Says this medicine failed at this point. Now this equal to what happens can happen with some biomedical device. So The sky is blue here. You can do literally anything you like if you go in this setting. This is another example of a project called Virtual Brain Twin Project. Now I'm going to show you one very interesting example. Now, success of this research, I just showed you these three slides, is depend on how good you can represent the brain. And when I say brain, of course, human brain is the most important one in this scenario. But I want to show you one brain which is, I'm going to mute this. Now this before I start playing, just give you a little idea what's happening here. Researcher from University of California able to map the whole fruit fly brain. Fruit fly is essentially a fly, a little bit look like a house fly, have more than 140,000 neurons. So those little neurons in the brain, and they were able to map all of those neurons. And once they map, they can run those neurons in a laptop like I'm using for presentation now, which is phenomenal itself because it's not possible a few years ago. And this company called Eon System, which is an AI system company, took that fruit fly brain, like a virtual brain, put into a virtual environment, or they call it simulated environment, and let the fruit fly do things how it fruit fly is supposed to do. In this case, fruit fly is not alive, by the way, but because the fruit fly got the brain, which is exactly copy of the fruit fly brain, the fruit fly in this virtual world behave like a real fruit fly, which is just amazing. This happened just a few months ago, by the way, so it's very, very new. See, let's see what's happening. By the way, you're gonna see the simulated environment fly here in this screen. And on the right side, you will see how brain is behaving. This is the fruit fly. Fruit fly is showing very much like a forging behavior, which is goal-oriented behavior to finding something. You see fruit fly is cleaning the face, which is called grooming behavior of the any fly. And they, in this case, also can do that, can eat the food, in this case, have certain behavior, certain phenomena. And it's just so phenomenal that someone can do that. And this virtual fly behaving exactly like how fruit fly behave. You might think, oh, I can write a if and else and simple program. No, it's not like that. It's an actual behavior representation. Now remove this fruit fly and put the human brain there, virtual human brain. Similar phenomena can be behave and predict in there. Fruit fly only have 140,000 neurons, so relatively small. Human brain have more neuron than how we call more than the stars out there. So complicated for human brain, but it's possible to simulate a part of the brain, like a hippocampus of this part of the brain, frontal, or like I say, cortex in the start. Another example I want to share is around special navigation. Now, why I highlighted this one is because um, special navigation is super important topic, which is there from long time. Let me explain this way. Navigation is most important part of our everyday activity. In case of you out there, you also go from your home to office almost every day. You remember where to take a turn, which way to walk, where to stop, which shop is where, those kind of information always there. And this is the part where our brain have something like a GPS embedded into brain, which is amazing. And this GPS is known as grid cell and the place cell. Essentially, these two type of the cell which do some sort of recording, like when you move around. It's like a GPS recording. It's like a Google GPS if you use Google GPS or some other kind of a GPS you use. They continuously record all the information. And this information recording is found by researcher a while ago. And when they found it, I think It's a work of a it's a last century essentially. Someone found that, and they received a Nobel Prize in 2000. I think it's 2014. They received a Nobel Prize of finding this GPS system in the brain. So it's so important angle. And someone who have this broken, this system doesn't work, or in other word, research suggests those who have poor navigation ability, there's a good chance for them to have something like a Alzheimer, something like a problem when they become older, they start forgetting things. So in other words, it's good to train yourself to navigate by yourself without GPS. It's a good thing for your brain and the body. Now, what I want to show you is this output. This is so much complex figure here, so don't worry about that. This is a paper from Google DeepMind. What they did, they created a virtual brain and put on AI agent and see how it behaves. Now, this virtual brain represents the mouse, so it's not a fruit fly. And what they did after whatever the experiment they run, the experiment is about make the mouse do navigation, go from here, there, in the environment. Um, and once the mouse did the navigation within the virtual brain, they were able to see something like this. If you see on my screen, let me change back to laser pointer. Now this is very similar to how real mouse behave. Now, what essentially I'm trying to say, they did this experiment virtually, automated. So they just run and left it and go away. And and when they come back, they were able to get the output from the research, which look like this. These output represent what I said before, grid cell and the place cell, very much like that. This is the very similar output if it's a real mouse in the real world behave. So essentially what they showed in their research paper, which is just 4 years after the Nobel Prize, is their virtual brain and AI agent can produce the same result, which is a biologically someone who got a Nobel Prize just 4 years earlier showed by several years of experimentation. And they did in a few hours, or I believe few days, not more than that. So this is like an excellent example how virtual brain and AI agent can work together. And I think this paper is phenomenal to show that. I haven't seen so much work more since then around this area, and something we are also doing in our lab, and who knows, maybe you get some very interesting output in very near future as well by doing this angle. Now, I'm getting closer toward the end, and I want to share. So where we heading with this all, right? You might be asking yourself question. If everything can be done by AI, if AI is doing research, AI is producing output, AI is writing research paper. In fact, there's all the major conference, which is about AI and machine learning, is also using a system to do review as well. So where is the human in this whole process? It sounds like a human is kind of detached more and more. And not to mention, AI is already affecting jobs, right? AI is affecting jobs for people from computer science, unfortunately, people like us. And AI is affecting job of software engineering. So many data suggest, at least from US, that there's a significant decline in number of students who want to go and study computer science because they don't know the future, how computer science might be going to look like. And they are not the researcher, obviously. But same apply to researcher as well. That if researcher go and do PhD, what the future look like? Because their PhD, which they spend several years, can be done in a short amount of time by a AI tool. So is it the worth of doing the PhD? Is it the worth of doing computer science degree? So obviously this question, not just computer science, is just unfortunately computer science is in the top in the list, but it apply to every field, biomedical or mechanical. Well, you might think mechanical required a hardware, very true, but there still is very skill-based approach. And anything which is systematic, have certain way of doing things, highly likely can be automated with AI uh, in coming future. Now, so question is, what future researcher going to do with respect to AI? What they're supposed to do? Where we are heading into? I think, not to mention, I think this is a very obvious answer. We may be going to take the back seat instead of front seat to orchestra all the things we want from AI to do, and AI is able to do those whole thing multiple time in short amount of time. So in some way, actually, it's a good thing, because now instead of spending on one topic doing research for 5 years, and you get an output and you feel like it's not the best output I want, but anyway, you already spent 5 years, so you move on. You can repeat multiple times in short amount of time until you reach a point which is a lot more in the right direction, a lot more have a depth, and so on. Why? Because you can ask better questions now. Your AI agent may be able to search, code, synthesize, and simulate so quickly that you can't. And this could be several times repeated until you get the right output. And then you can also discard everything and start again, which is the freedom essentially you have. That means we that means 10 researchers in the past repeat 10 different way of same research and that get the output. One researcher can represent that 10 easily in few days to a few months to a few years. So in some way, if you think about the more positive angle, that now the whole quality can improve suddenly very quickly. But not to mention we are losing a certain skill set. Maybe we don't know exactly what happened behind the scene because our AI tool is taking care of that job for us. Although, regardless what AI can do all the time, I think the judging the validity, plausibility, and reproducibility of the output from AI is still held by us, because AI can validate, yes, maybe it tells you, okay, this looks like a best solution, but in the end of the day, you are the one who's tell, okay, this looks like a very good solution, very good idea to move ahead. And also reproducibility fall onto you, because whatever research we do is very important. It can be reproduced by someone else can repeat that. And among this all, I think that this is the most important one: accountability. As a researcher, use AI, use virtual brain, whatever, but in the end of the day, your name is attached to the research. That means you are the one who's going to take accountability. If something goes right, great. If something goes wrong, also on you, not on AI. Now, this is not going to go away anytime soon, but who knows, very near future, there may be laws and regulation around this, that AI generated word is shared accountability between AI tool and the human. I think those who have domain expertise and knowledge will be most benefit from this kind of a work. For example, I know when I was doing research, people who do not know coding, programming, they really have hard time to do certain things. Now that's not so much a case, because they can move ahead on that barrier so quickly. And I do think when we have this automated research, and like I give you an example of 10 PhD student, and maybe out of 10, two are not so critical thinker, because of this system, they will be filtered out. So, unfortunately, not so much place for those who can't critically think anymore if we move ahead in this direction. To summarize, I think there are three big paradigm of research are visible already: agent-based, human and agent-based, and virtual human and agent-based. Agent-based and human and agent kind of already there, especially agent-based already there. Two of them remaining are growing faster as well. And I think this is the ultimate future. Like I say, agent-based have significant progress, already disrupting research world out there. Human agent is becoming more and more into the world coming there, because there's lots of things exist around that. You can fine tune, you can create a system, and so on. And when I talk about virtual human and agent, this is essentially a real future of automated research. Maybe this virtual brain not virtual so anymore, maybe it's a actual your brain can be uploaded online and do the research. And the last bit, I think future researcher can do, of course, automated research by not doing so much manual work and more focus on framing the question, validating, orchestrating the whole automated system. That's the way we heading into as we moving forward in this direction. Um, this work I am doing here in UTS, of course, required a lot of funds here and there, and thanks to all these organizations who fund all the time here and from different year, different time to fund my research. And of course, my student and colleagues, some of them listed here, not all of them though. And with this, thank you for listening.
Thank you so much, sir, for this valuable session. Me, at
Happy
least,
to have
learned
any
a lot of
questions.
things.
Yes.
If anyone, if anyone has any kind of question, please ask. Is there any questions?
Even they can write on the chat box.
Yeah. Okay.
Yes, please drop your question in the chat box.
Sajal, we can
So
proceed.
anything to- yes,
Is
sir, I
there
think
any
there is.
question? Is there any question in chat box?
No, sir, there is no any question in the
We
chat
can
box.
proceed. We can proceed.
Okay, sir. Then moving towards the conclusion of this session, I would like to invite Ms. Sadhna Yadav ma'am for the vote of thanks.
Thank you, Sajal. Thank you so much, sir. Your session gave us a fascinating glimpse into the future of human AI collaboration, brain computer interface, and neuroadaptive technologies. The way you explained such advanced concepts with clarity and real world relevance made the session highly engaging and thought provoking for all of us. Your work in human augmentation, cognitive neuroscience, and AI driven innovation is truly inspiring for students, researchers, and faculty members. We are sincerely grateful for the valuable insights and knowledge you shared with us today. On behalf of the organizing committee and all the participants, I extend our heartfelt thanks to you, sir, for taking out your valuable time to guide and inspire us. It was truly an honor to have you with us today. Before we conclude, I would like to inform everyone that the next session will begin after lunch at 2:30 p.m. We kindly request all the participants to rejoin on time. Once again, thank you everyone. Have a wonderful day ahead. Thank you.
Thank you, Avinash ji. Thank you
Thank you,
for your
Nivas sir.
precious
And
time and such a nice lecture.
thank you. Thank you. Thank you for inviting me again. And thank you, everyone, for be patient and listening.
Thank you.
Thank you. Bye.